In the previous lectures, I have discussed the problem of point estimation. In the beginning, when we introduced the problem of statistical inference, we mentioned that there are two broad divisions of this topic. One is where we want to guess the value of a parameter or parametric function. This is called the problem of estimation, and in the estimation we had the problem of point estimation, where we specify a value which we call as an estimator, or sometimes we assign an interval which is called as an interval estimate or a confidence interval. However, there may be situations when we want to test some statement about the parametric function. So, for example, there is a medicine for treatment of a certain disease, and we know that the success rate of this medicine is say 3/4, like 0.75 or 75% of the patients who take this medicine, they get cured. Now, a drug manufacturer introduces an improvisation over this medicine, and he wants to introduce the medicine in the market. Now, certainly he will be interested to know whether the new medicine is more effective. Suppose I say P is the proportion of the patients who get cured using this new medicine. Then the question that obviously one has to ask, whether P is greater than 0.75. So, now this problem now you can formulate in a statistical way in this following fashion. Suppose in general n patients are there, n patients are given the treatment or medicine, and P is the observed proportion, x is the number of patients getting successfully cured using this treatment. Then we can say that x follows binomial n p distribution, and we want to test the hypothesis. We use the notation H for a hypothesis, p is greater than 0.75. Similarly, let me state another problem. Suppose we want to compare the average age at death, that is called longevity, of males in two ethnic populations. In a country. So, let us say there are two ethnic populations. Let me call this population say pi 1 and pi 2, and let mu 1 denote the average age at death in population pi 1, and mu 2 is the average age at death in population pi 2. Then we are interested in testing hypothesis, say whether mu 1 is less than mu 2. We may like to test whether mu 1 is equal to mu 2. We may like to test whether mu 1 is greater than mu 2. We may like to test whether mu 1 is not equal to mu 2. Let me give some names to these hypotheses, say H 1, H 2, H 3, H 4. Now, to put it in the statistical framework, we will assume that the ages at death in the two populations follow certain distribution. We may assume here, so we may assume some distribution for the age at death in pi 1 as say, let me call it f 1 mu 1, and same thing assume in pi 2 you assume as say f 2 mu 2, and then we are testing the hypothesis whether mu 1 is equal to mu 2 or mu 1 less than mu 2 or mu 1 not equal to mu 2, etc. Suppose, so basically what we are doing, what is a statistical hypothesis then? A hypothesis, a statement about the parameters of a population. For example, here I am considering binomial distribution and we are making a statement that p is greater than 0.75. Similarly, here we may be considering two populations say f 1 and f 2. Of course, we may take them as normal populations or exponential populations or gamma populations, and then we are checking about a statement about the parameters. We are making a statement about the relationship between the parameters here. So, broadly speaking, then we can say that a statistical hypothesis is an assertion about the, actually here we have given the example where we are making a statement about the parameter, but we may also consider something like this. We want to find out the distribution of incomes. So, we may like to check whether the distribution of incomes follows a Pareto distribution or the distribution of the incomes follows some other distribution. So, in that case we are checking the form of the distribution itself. So, in general a statistical hypothesis is an assertion about the probability distribution of population. So, it could be one population, it could be more than one population also. Let us consider, suppose we use two different measuring devices to measure an experimental result. So, some outcome is there from the experiment and we are using two different measuring devices. Now, the results of the two devices may be the same. However, there may be more or less variability in one than the other. So, if we assume that the measurements taken from two devices follow say normal mu sigma 1 square and normal mu sigma 2 square distributions, then we want to test say sigma 1 square is equal to sigma 2 square, or we may like to test say sigma 1 square is not equal to sigma 2 square, or we like to test say whether sigma 1 square is less than sigma 2 square, etc. So, these are statements about the parameters of the distribution. Now, we introduce what is called a null hypothesis or a composite hypothesis, sorry, alternative hypothesis. Now, in the examples that I have described here, for example, we wanted to check whether the average longevity or average age at death in the two ethnic populations is the same. Now, this statement may not be true, this may be true. Similarly, in the problem of introducing a new medicine in the market for curing a certain disease, we introduced the hypothesis whether p is greater than 0.75. Now, it may be possible that p is greater than 0.75 or it could be that p is less than or equal to 0.75, or we may say p is equal to 0.75 or p is equal to 0.95 or p is equal to 0.9. So, when we make an initial assumption about the probability distribution, that we call as a null hypothesis. So, we may take a decision whether to accept the null hypothesis or to reject the null hypothesis. So, a null hypothesis is the, you can say, tentative or the first specification about the probability model. So, a null hypothesis is a first or you can say tentative specification about the probability model. So, for example, we may say h p is equal to 0.75, we may say h mu 1 is equal to mu 2, we may say h sigma 1 square is equal to sigma 2 square. So, this is called a null hypothesis. Usual notation in the standard books is used h naught here. Now, when we specify a null hypothesis, we also specify an alternative hypothesis to check that if this null hypothesis is rejected, then what is the other possibility. That specification of another hypothesis in contrast to the null hypothesis, that is called an alternative hypothesis. For example, in this problem we may say p is greater than 0.75, here we may say mu 1 is not equal to mu 2, here we may say sigma 1 square is less than sigma 2 square. So, certainly the general specification can be like this. Suppose we are considering probability model p theta, where theta belongs to a parameter space theta. Then let us consider two subsets, let me call theta naught as a subset of theta and theta 1 as a subset of theta, such that theta naught and theta 1 they are disjoint. Then we may set up the null hypothesis and the alternative hypothesis as. So, this is a problem of testing of hypothesis. For example, in this case your theta naught will become equal to the singleton set 0.75 and theta 1 will become the set 0.75 to 1. In this case, this is the parameter space, here is a two dimensional space, mu 1 is equal to mu 2 is the line. So, the theta naught is this line and all other place this is actually theta 1. In this particular case, we are dealing with the positive half, sigma 1 square is equal to sigma 2 square is this and sigma 1 square less than sigma 2 square is this. So, this is theta naught and this is theta 1. So, the null hypothesis and the alternative hypothesis specify the parameters to be in two distinct parameter spaces. Basically, we are specifying the family here. We can also say if P is the probability distribution, then we can say it belongs to the family P theta, theta belonging to theta naught, or here we can say P belongs to P theta, theta belonging to theta 1. So, the null hypothesis and the alternative hypothesis, they usually divide the parameter space into two complementary regions. Now, the way I have explained here, it is not necessary that the two regions exhaust the full possibility. For example, in this case the union of theta naught and theta 1, that is not the full parameter space. For example, the binomial distribution theta is actually 0 1, but the union of these two is not this. In this particular case, the union will be equal to the full two dimensional space. Once again, in the third problem, the union of these two is only half plane here, half of the first quadrant. So, we may take the null and alternative hypothesis as completely complementary regions, or sometimes they will be only disjoint, but need not be completely complementary. That means, they may not exhaust the full space. Then what is the test of statistical hypothesis? So, a test of statistical hypothesis is a procedure to decide whether to accept or reject the null hypothesis. So, usually what we do, we take a random sample, we take observations from the given population, and based on this we take the decision to accept or reject H naught, say. See, for example, consider say a die. Okay. Suppose we are consider a fair die, consider a die, we do not know whether it is fair or not, and consider say P is the probability of occurrence of a 6. Okay. Then we would like to check whether P is equal to 1 by 6 or not. Then we may take a decision based on certain experiment. Suppose we conduct the experiment, we toss the die say a certain number of times, say n times. Okay. Let me put n is equal to some number here, suppose I put 60. Okay. Then we may say that if, and here let x denote the number of 6s. Okay. So, if x is say 9, 10, 11, we accept H naught, and if x is not equal to these numbers, then we accept H 1, or you can say reject H naught. Then this is a test procedure, because what we are doing is based on the sample we are taking a decision whether to accept H naught or to reject H naught. Here I would like to clarify, when we say that we accept H naught or we reject H naught, then these statements do not have the validity of a truth. For example, if I say that x is equal to 9, 10, 11, then we accept H naught. It does not mean that p is equal to 1 by 6. It simply means that based on our test procedure, we are in favor of hypothesis H naught. Similarly, if I observe that x is different from 9, 10 and 11, then we conclude here that H 1 is more plausible. It does not mean that H 1 is actually true. It means that based on the sample, we do not feel that H naught is a correct hypothesis, we feel that H 1 is more plausible. So, acceptance or rejection of a hypothesis based on the sample has only a circumstantial validity. That means, based on the observations we are making a decision whether to accept or reject a given hypothesis. These are not the assertions about the truthfulness about these hypotheses. Okay. So, that is why this is called only a statistical test or a statistical hypothesis test. Now, the theory that we are going to discuss in the beginning, that is known as the Neyman-Pearson theory of testing of hypothesis. There are some alternating theories also, but I am going to discuss this particular theory here. In this theory, it is essential to specify a null hypothesis and an alternative hypothesis. There are some other approaches where only the hypothesis for which we are initially interested will be enough. So, I will be continuing this in the next lecture.